We've had quite a few questions coming through the YouTube chat, and they kind of start in a historical 40 million years ago to what we can do in the future. So I'm going to try and like follow a bit of a timeline. So we'll start with Emma's question. What was responsible for the high temperatures 40 million years ago? Was it volcanic activity or I guess something else?
So it's so one of the big changes is changes in the distance of the Earth from the Sun. So it can be driven because there's that link between temperature and climate. A lot of the changes that we see in the past were driven by changes in temperature because of changes in the way the way the Earth was behaving, and so that then led to changes in CO2 as well. Whereas this time around we're changing the CO2 and that's changing the climate. So. I don't know. I mean, I'm not sure of the precise details of 40 million years ago because I don't know. I'm not an expert in paleoclimate, but it's those sorts of changes that give rise to that.
That actually links to a question that I had for later, but I might link to it now. Somebody mentioned about solar cycles and their effect on climate readings. Where is it? Well, that'd be good if I could find it. Basically, they said that at the moment we're going through, here we go. So do the models take into account solar cycles and activities? Because at the moment they're much less active than usual. And so the climate would be cooler than it would otherwise be. And do these models take that into account?
So no, I can't actually remember whether the specific models that I showed you include that effect, but it certainly has been included, and I'm pretty sure they do actually. It's certainly been looked at what impact the solar cycle has. It does have, there's an 11-year cycle, for example, and there are longer cycles as well, but it certainly does have an impact, but it doesn't have an impact that fits with the observed change. So that's and we do see impacts in the weather in the UK, for example, with the solar cycle, because it can change the way that kind of interaction between the polar weather and the European weather happens. So there are signals when you look at seasonal forecasts that you see that where the solar cycle has an impact, but amongst a number of other things. So but on the sorts of things that I've been showing, it's one of those fingerprints that I mentioned that we can look at. We can look at the fingerprints of some of these different natural things and some of the man-made things, and we can see the differences. So it is certainly something that's been clearly looked at.
That's really fascinating. I'd never have thought of including that. So,
yes. Yes, and there's also an inclusion of a kind of general background effect of volcanic eruptions because they produce a lot of aerosol. You remember I mentioned these particles produced by power stations and things, but there's huge amounts produced by volcanoes as well, and they cool the climate. So if you look, if I reshowed that temperature graph, you'll see a drop in temperature in 1992, for example, when there was a big volcanic eruption in the tropics, because a lot of aerosol ended up in the stratosphere and it stayed there for about a year or so. And because it was in the tropics, it can get into the stratosphere more easily. So that had an impact as well. So all those things get taken into account.
It's not an easy job, this climate modelling, is it?
It's not, no.
Lawrence asked, does cloud cover have a net cooling or warming effect, or is this dependent on the circumstances?
It's dependent on the circumstances. So the high cloud tends to let through the solar radiation. So if you think about the kind of thin cirrus cloud that you see on a sunny day, just this very thin wispy cloud, that lets through a lot of the sunlight, but it doesn't let out the infrared radiation, so that tends to trap heat in the atmosphere. Whereas the low cloud, if you think on a cloudy day, that's very low cloud, tends to stop the solar radiation getting through. So it's critically dependent, the distribution of cloud. So one of the things that climate models do is, modelers do rather, is to really try to understand whether so you can look at whether you're getting the right balance in the atmosphere by looking at how much radiation is at the top of the atmosphere, but you can get the right answer for the wrong reason by having the wrong distribution of cloud. And if you do that, you'll get the wrong answer when you try to look at climate change because the processes are wrong. So one of the things they do is use satellite measurements to try and understand what the cloud should look like and how that, and of course we don't measure, it is complex because we don't measure the clouds directly. We measure the what we call the radiance, and we measure the radiation coming from the clouds. And so what we then do is use the model to kind of simulate that radiance. So it's quite a complex process. because the thing that you want to measure, you can't measure. You have to measure something that's related to it. Now, because we understand that well, we can get a good handle on it, but it makes it, it's more work, if you like, in order to be able to do that properly.
Speaking of trying to relate measurements to things, Richard asks, how confident are we that measurements from ice cores correlate with current atmospheric readings?
So that's a good question. I'm not sure I know the answer to that, but you can obviously compare the historical record with the recent ice cores. I think there are difficulties with some of these prehistoric measurements, because with ice particularly, I believe, because it compacts over time. So some types of measurements are less easy to use in the more recent past. But there obviously has been a lot of work done to make sure that you can make those linkages. I mean, whenever you're comparing different types of observations, you want to have an overlap between the observation data sets so that you can correlate between them. And the same thing happens in the recent record, where we compare different satellites, for example. Our early satellite measurements were very crude. They've changed over time, and they obviously, weather forecasters want us to improve the measurements all the time. Climate model people would like them to stay the same, but that's not going to happen. So what you have to do is have an overlap between those satellites, and so you can compare the two satellites and make sure when you see a jump in the temperature curve, it's not just a change of instrument, it's actually, you're actually measuring something. But obviously with these kind of proxy data sets, that's more difficult, but there's a lot of work done in this area to make sure that they have got a handle on that.
Keeping in that part of the world, Arctic and Antarctic regions, is there sufficient data being gathered in the Arctic and Antarctic regions to calibrate the modelling in these regions?
So there's a lot more. I mean, this has increased over time. That, for example, there are now satellites that can measure the amount of ice. And the difficulty with ice measurements from space is that, of course, a lot of the time you're just measuring the area of the ice, and you really need to understand the thickness of it as well, but they can get a handle on that now as well. So there's more and more information available to help us to do this. But there's never enough information. I mean, if you ask any scientist if they've got enough information to give you a definitive answer to anything, they'll always tell you they need more information and more understanding. That is inevitable. But there are, areas which are difficult to get to and difficult to measure, obviously are much more difficult. And the ice processes are very complex. I mean, one of the things that we've seen in some places is bits of ice sheet breaking off and into the sea. And that can be quite a rapid process, and understanding how that process works and whether it might accelerate, or for example, when you've got ice that's close to the coast, it can break off and go into the sea, but if it's not close to the coast, it won't do that, so it might behave rather differently once it's retreated. So all of those things you need to understand. So it's one of the things I think in that new model I mentioned, which I didn't go into in detail, was that the ice processes have been significantly improved to try and get a better handle on that.
S. McNeil asks something that links to ice going into the sea. What increase in sea level is already locked in due to increasing temperature causing the seawater to expand, never mind any contribution from melting ice caps?
That's a good question. I'm not sure exactly what the numbers are. I'd have to look those up. But yes, because there are. He's absolutely right. There are two parts. There's just the ocean, the water expanding because it's getting warmer, and then there's the ice melting and going into that. And I think in terms of the projections, which obviously include the stuff that's stored already and the increases that are going to be over the next 100 years, I think it's about half and half, but I'm not sure. And I think one of the things, this is a slight diversion, but one of the things that was done, for example, for looking at the replacement of the Thames Barrier, was to look at, and there's been a series of studies done on this, was to look at what because the IPCC report doesn't give a very clear handle on how much, what the worst case scenario could be of ice melting, because there is such a difficulty in understanding the physics of the ice, as I mentioned before. So what they did was to look at the worst case scenario. What's plausible that could happen if the worst happened and large chunks of ice came off? And so they were able to look at that worst case. And I think you're looking at around a 2 meter rise in sea level, which is more than twice as much as what they're actually projecting. But that's something you can look at, you can flag that and say, well, we'll plan our defences on the basis of 0.5 to 1 metre, and then as we go forward in time and we learn more and we see more change, we'll be able to adapt that and maybe make a change in the future. So it just gives you that signal that you need to adapt. It's what they call adaptive adaptation. So it allows you to make a decision in the absence of perfect information. So what you're doing is you're saying, I'm making a decision now, but I'm recognizing that in 20 years' time or 10 years' time, I might have to alter that decision and do something different. And the COVID is an excellent example of that. I think we're doing it every day actually with COVID at the moment, but that's an illustration. Is the ministers keep getting up and saying, well, the information's changed, we have to make a different decision, and that is the reality of the situation. You can argue about when they should do it, but it's you're having to adapt to new information. What you have to do, of course, is make sure you collect the right information and do the projections so you can get that understanding, so you know how to respond.
That seems like something that escapes people's mind when they think of science or like topics in general, that we do have to adapt to things that we may think we've figured out, but then it has to change in like 10 or 20 years, as you said. So Pete asks, do our current climate models reflect an increase in the trend to warmer and wetter winters in the UK as a result of the loss of sea and ice caps in the Arctic, and is it a feedback loop?
So the warmer, wetter winters are to do with the fact that the global temperature is increasing and that we're getting more rainfall because of the water vapor feedback. So if you look at globally, we see overall more rainfall. We also see more droughts as well, but on average we see more rainfall because the water cycle is more active. But because it's more active, where it's dry, it's also drier because you get sinking motion and drying and so on. So the pattern in the UK is somewhat similar to that, but it's also dependent on what's happening with our storms and storm tracks. So a lot of the rainfall that we get is associated with big weather events and heavy rainfall during fronts coming through and that sort of thing. And so that's what we're seeing. We're not seeing, and we also see changes. So one of the things if you look on a shorter timescale, so maybe from 1 year to the next or from 1 decade to the next, we see changes in the kind of average position of the jet stream, and that means we get some winters where we get lots of storms and some winters where we get perhaps a very cold winter. 2010, I think there's an example of this where we had very few storms. It was very cold. Because the jet stream went in a different direction, and when we had the big cold winds coming from the north, and that was reflected in some of the natural changes that happen on that kind of decadal timescale. So there are natural changes that happen on these kind of year to decade timescales that overlay the kind of long-term trend that we're seeing. But it's largely around that. So the melting of the ice caps would mostly affect the sea level rise. What it can do is the Arctic ice, the big increases in that can affect the European weather. So there are links to, so we think that paradoxically we could get periods where we get more cold winters with the initial reductions in sea ice because of the changes in weather pattern associated with that. So again, it's a complex system. But those changes would be temporary. Obviously, as the temperatures increase, it would get warmer as well.
So I've seen my colleague Dave sneak up into the comments, not sneak, he was there anyway, and answering some questions as well, because he worked on the Christmas lecture, so he's been answering people. But he did ask a question from my meteorologist wife: could climate changes move the Gulf Stream and make Britain more like northern Norway or southern Spain? So
the Gulf Stream is the kind of surface current, what we call the thermohaline circulation, which underpins that. Yes, there are that has changed in the past. So big changes in climate, in Europe have been associated with the collapse of that thermohaline circulation, and that's associated with changes in the saltiness of the ocean at high latitudes. So it's the balance of temperatures and the saltiness of the ocean that affects those currents. And so that could lead to, if that happened, we tend to get warm, mild climate because we've got that circulation there. If that collapsed, then it would get much colder. So there was a very silly film brought out, I think it was about 15 years ago now. What was it, the Day After Tomorrow, which hypothesized this. I wouldn't recommend it as a film, but you know, everything froze up, and you know, it was that was kind of premised on that. But we think that that's very unlikely by the end of this century, but it could happen in the future, and that would lead to cooling in some parts of the world, yes, and Europe in particular.
Okay. Carnan has asked, how do you tackle the input parameter uncertainty in the climate model?
So that's a very good question. So when I showed the climate projections for the UK. So one of the things that was done there was to look at exactly that. So I mentioned, just for those of you who are not scientists, that we have to average, we have to what we call parameterize a lot of the processes in the model. So the clouds, for example, we can't represent the details of clouds, so we have to represent the average properties of the cloud. And there are lots of parameters that you use in that average representation, and some of those are a qualitative judgment as to what you think they should be. You do obviously run your model and assess it against the real world, so that you can adjust those numbers to as close as possible to you think as reality. But there are some uncertainties there. So one of the things that we do in the climate projections is to vary those parameters in order to create possible different futures. So the climate projections, the UK climate projections in 2009 and in 2018, it did exactly that. And they produced probability distributions, which basically say, these are all possible climate models because we don't understand the full details. And this gives us an idea of the range of possible outcomes. So it gives you those sort of scenarios. That's how that's done. I mean, in terms of, but obviously in terms of creating the kind of baseline model, we do pick numbers that give something that can reproduce the past climate, but we've only got one past climate to test it against. So, you know, so we have limit, you know, there are limits in the information that we have.
Matthew asks, does human forcing mean GHGs? Is either GHGES or GHGs emissions, or are there other factors at play, e.g. land use?
Yes, there are. That's a good question. So we've got, I mentioned carbon dioxide, methane. I also mentioned that there are other gases and particles that are important, like the particles that are produced, the pollution particles that are affecting human health, things like nitrous oxides and so on. And those all have an impact on the climate. In terms of producing those chemical species, you know, we're producing them by burning fossil fuels. We're also producing them by changing the way we use land, and we've obviously been doing that much longer than the Industrial Revolution, although obviously it's on a larger scale as populations have increased. So if you chop down forests, for example, then you release a lot of carbon in the atmosphere, both from the forest itself, but also because you degrade the soil, and soil is a very good way of absorbing carbon. So there are lots of ways that we can actually help to mitigate climate change by managing landscapes better, both in agriculture and in non-agriculture landscapes. And so there are big, obviously, pushes to do that. And you know, some people will say, oh, you know, producing meat is bad because it produces a lot of greenhouse gas. But actually, you can improve the way that you do that in a way that actually reduces the amount of greenhouse gas that's produced. And I think there's still a lot of work that needs to be done to understand that. I was talking to somebody recently who was talking about rice production, which is often criticized for producing a lot of methane because they grow it in, obviously, rice paddies, a lot of places with a lot of water. If you grow it in drier conditions, obviously still with water, but not flooded, you don't produce the methane. So in fact, you can do that in a much more carbon neutral way. So there's lots of things you can do with farming. It's very clear that wild landscapes can be very beneficial for climate change, as well as obviously biodiversity and other things. There's an example behind me, actually, which is Romania, where they farm their land in the traditional ways. That's actually a meadow, which is then cut for the hay, and they feed that to the animals, and they produce the best milk I've ever tasted. So I thought that was a good background to have for this talk. So. But land use, I think, is a really important issue, and I think a lot more attention could be paid to how we use land and how we can use that to help us. And of course, that is done in the context of the Sustainable Development Goals. We need to produce food as well, and we need to protect biodiversity. So it's a really good illustration of where we need to look at the problem in the round.
I just realised if I was more awake and on it, GHGs is greenhouse gases. So sorry, Matthew,
Yes, right.
that was my fault. I've got pandemic brain. Pete asks, are we seeing an increase in an average of temperatures in 2020 due to less aerosols in the atmosphere, due to the drop of industrial activity, in brackets COVID, and if so, how much?
So I don't know the answer to that. What I do know is that when you look at the late 20th century, you can do those graphs I showed, which showed the temperature increases. If you do the greenhouse gases separately to the aerosols actually contribute to quite a bit of cooling. I should say that in terms of the numbers, that there are still big uncertainties in the aerosol cooling, and there are big uncertainties in the amount, how the aerosol affects the cloud. I mean, I've already described the complexities of modelling clouds. You can understand that. And some of the recent models actually show quite a lot more warming from the greenhouse gases and a lot more cooling from the aerosols. And if that's the case, then actually we're in for quite a lot more warming than was being predicted before. So people are very much active in trying to understand that for the next IPCC report. So I think one of the things that will come out in that report will be trying to unravel that, and whether the models are telling us something really important or whether they're still missing something. In terms of the actual numbers for 2020, I don't know the answer to that, but it will be somewhere on the web, I'm sure. Or maybe somebody in the audience will be able to post it in the comments. I don't know.
Oh, yeah, I mean, there is a bit of a lag, but I'll pop back afterwards, and if anyone's got an answer, I will search for it. We've had a couple of questions basically looking into the future. Garth has asked, do you think that direct carbon capture at scale is realistic, or do we need to just stop burning fossil fuels, plant more trees, protect peatland, etc., etc.?
So I mean, I think we need to see demonstration of carbon capture. It's that there is some carbon capture demonstrator, because it's used actually paradoxically to allow you to extract more oil. Because if you force CO2 in underground, you can force out the oil that's left in your oil well. So it has been used, but it hasn't been used in the way that we're talking about. So I'd want to see it demonstrated. I think nuclear is probably part of the solution as well, and there are lots of different types of nuclear technology which haven't really been tested at scale yet. One example is thorium, for example, which was tested in the 1950s but abandoned because it didn't produce weapons-grade uranium. But of course, our driver now is not to produce weapons-grade uranium; it's to produce low carbon energy, and that's much less dangerous than other forms. So we need to look at all. And we need to look at all of these different solutions objectively, and not with any prejudgment about them. So equally, I would say with carbon capture, I shouldn't prejudge it. I don't know the answer, but I think the problem is we're not doing the testing at scale. So we need to test some of these things, but certainly we need to look at all options. And I think land use is something we should be, and is being looked at, but I think it needs to be looked at seriously as well. So one thing I would say is that renewables, things like wind and solar, if you increase those, you do also need to increase your gas use initially, because you need something that can switch on and off for the times when the sun's not shining and the wind's not blowing. So I believe, there was a good TED talk on this actually. Now, of course, everybody has an agenda when they give these talks, but it was quite convincing to me, which showed that in Germany, when they they shut down all their nuclear power stations after the accident in Japan, and their carbon dioxide emissions went up because they had to increase their gas use to compensate. And they've got a lot of renewable energy. They increased their renewable energy substantially, their wind and solar, and in order to balance that, they had to have gas. So if you're going to do that, then you need carbon capture and storage, obviously, to go with it. So that's why I think it remains to be an open question. I think what I would say is that the assumptions that are made in the 1.5 and the 2 degree reports about what you can do need to be looked at in the cold light of day to say, which of these are actually feasible and which of these are theoretically feasible, because they're not the same thing.
Oh, that's interesting. You've kind of half answered Bruce's question, because he asked, what is your view on nuclear power, and also the prospects of fusion in particular?
So I'm not an expert, As I say, I think we need to look at all technologies and get the information. And it's all very well saying we don't have the technology to work at scale, but you've got to start sometime. Fusion is always one of those things that's 50 years away. I don't know whether people are saying it's closer now, but
it always seems it's 50 years.
I don't know. But I think what we need to do is unleash the technologies and allow people to test some of these things and create the environments where people can test them. I think the difficulty with innovation in an energy space is that it's really expensive and potentially really damaging if you get it wrong, because so it's not like the explosion in what happened in the internet, which people could develop stuff in their back bedrooms and then put it out to the world. You can't do that with this very easily. So it does require government intervention or at least governments to create the environment where industry can invent. But I think we've shown how creative and inventive people can be. I mean, during the COVID crisis, the rapid development of vaccines and so on, completely new technologies has happened. These things can be done, and we just need to put. I think we don't have the immediacy for climate change. That's the problem, because the impact feels like it's a long way off. But actually, you need to make. It's such a big change that you need to put the investment in sooner.
No, I agree. It's been interesting seeing how we can be like put call to action, and like everyone has, if everyone has one agenda and one like target that they're reaching for, but climate change doesn't seem to capture people quite like that, like it should. Garth has also asked, with the advent of supercomputers and quantum computing, are forecasts still going to be significantly subject to chaos theory? Also, the advent of multiple satellites and other sensors must help.
Yeah, so all these things help, but chaos theory is chaos theory. It doesn't go away. And the other problem with the computers is that they are, Moore's law is that computing will increase in power, double in power every one and a half years, every 18 months, and that's breaking down. So in fact, what the big climate and weather centers are finding is they're having to spend much more money on computing next time around in order to get the increase in scale that they need to do better, to do weather forecasting better, to do climate better. And one of the things that they do for weather forecast, I mean, I think this is particularly relevant for weather forecasting, is these probability forecasts. So they do a whole, instead of just doing one forecast, they do 20 or whatever, and then they can look at the range of possible outcomes and give you an idea of the probability of what weather's going to happen. So it's rather similar to what I described with the climate model, where we in that case we vary the parameters. They tend not to do that. Some models do that, but you can vary the initial conditions to get the variation. But the problem with that is that you've then got to interpret that in a way that the public can use. And well, if you look at the Met Office weather app or any other app, actually, you'll see that up for rainfall, particularly, they give a probability of rainfall. And people actually say, they look at that and they say, oh, it's going to rain, it's not going to rain. Well, that's actually not what it says. So they might say it's a 10% chance of, and I do this, it says there's a 10% chance of rain. Well, therefore, I'm not going to take my umbrella. I do know if it says there's a less than 5, it never says 0 on the Met Office app. Yes. Less than 5 is the minimum. So I don't take my umbrella then. But it is a probability. It's not telling you exactly what's going to happen. So one of the problems is that we can use all this technology to give us a really interesting, complex answer, but how do we communicate that in a way that's useful to people? So that I think that's as much of an issue as actually solving the science problems. Actually, is making sure that we can interpret the information in a way that's useful.